1 and Calc 2, I will go ahead and solve some problems today out of Chapter 10 as a review. Meaning what? Meaning that you have section 10.1 followed by 10.2 followed by 10.4. These were the required sections, but I'm putting the material all together as a compact set. So we cannot artificially cut between, as I told you, cut between the sections. One thing that I did not work examples on, trusting that you remember it, was integration. In particular, I didn't cover integration of vector value functions and examples that are very, very important. Now, do you need to learn something special for that? No, but just like you cannot learn organic chemistry without knowing inorganic chemistry, then you cannot know how to integrate a vector value function, r prime of t to get r of t, unless you know calculus 1 and calculus 2, right? So let's see first a bunch of formulas that you use going back to last week's knowledge. What have we learned? We worked with regular curves in R3, and in particular, if they are part of R2, they are plane curves. I'm going to encourage you to ask questions about the example, but not now. In the review session we have on applications today from 2 to 3. What was a regular curve? Is anybody willing to tell me what a regular curve was? Was a vector valued function. Do you like big R or little r? It doesn't matter. Big R of t, vector valued function, x of t. Well, you know, I told you that sometimes we use bracket here. Sometimes we use round parentheses, depending how you represent a vector in R3. In our book, they use brackets, but in other calculus books, they use round triple, like round parentheses around that. So these are the coordinates of the moving particle in time. Doesn't have to be a specific object. It could be a fly, it could be just a particle, anything in physics. In physical motion between this point A of t equals A and B of t equals B. So at time A and time B, you were there. What have we learned? We've learned that a regular curve means practically it's differentiable and the derivative is continuous. It's a C1 function, and what else? The derivative of the position vector called velocity never vanishes. So it's different from 0 for every t in the interval that you take, like a. That's a regular curve. Regular curve was something we talked about at least 5 times. The point is, how do we see the backwards process? That means if somebody gives you the velocity of a vector curve, they ask you for the position vector. So let's see example, integration example 1 says I give you the velocity vector for a certain law of motion that I don't know. I just know the velocity vector as being 1 over 1 plus t squared, comma, shall I put a brace here, an angular bracket, 1 over 1 plus t squared, and here I'm going to put cosine of 2t, and t squared plus e to the minus t. And somebody says, that's all I know. For t on an arbitrary real interval, and we know v as a 0 as being given. Let's say it's given as 0 0, and that takes a little bit of thinking. I don't know. How about minus 1, no, 1, which would be just k. Using this velocity vector, find me the law of motion, which means find the position vector corresponding to this velocity vector. What is this? It's actually a initial value.
When you plug 0 in, don't you get 1, 1, and 1?
0, what is it? When you place 0 in?
Yeah, you get 1, 1.
That,
Are these the initial conditions for the location or the velocity?
I'm sorry, I wrote our the initial condition for the location. Thank you so much, okay? I probably would have realized it as soon as possible. Not the initial velocity I wanted to give you, but the initial position. All right, so how do I get to the R of t? I will simply integrate, and when I integrate, I have to keep in mind that I have to add the constants, right? Okay, so from V is our ln of t. It follows that R will be, who tells me? Do you guys remember the integral of 1 plus t squared as a...
Tan inverse.
So that's tan inverse, or I'll write it arctan, and I'm very happy you remember that. There are many students who don't. If you feel you don't, that means that you have to open the book where between chapters 5 and chapter 7, you have all the integration chapters, the main ones over there. It's a function defined on the whole real interval, so I don't care to worry about it. This is what we call an IVP, initial value problem. So what kind of problem is that? It's a problem like somebody would give you, knowing that f prime of t is little f, and knowing that big F of 0 is the initial value for your function, find f in general. So you have actually a initial value problem of the types that you've seen in previous classes. Arctangent of t plus c1, and then if you miss the c1 in general, this can mess up the whole thing because see, in your case, you're really lucky. If you plug in the 0 here, what you're going to have? You're going to have arctangent of 0, and that is 0. So in that case, C1 is just 0, and it's really nice, and if you forgot it, it would not be the end of the world. But if you forgot it in general, it would be a big problem. So don't forget about constant. When you the family of antiderivatives of cosine 2t. I know you know it. 1/2 sine 2t. Am I done? No, I should say plus C2. And finally, the family of antiderivatives of t squared plus e to the minus t.
2t minus e to the negative t.
Integral of. So what's the integral of? Huh? T cubed over 3 minus, excellent. Now, one of you guys almost killed me during the weekend, but that's okay. I mean, his problem had something to do with e to the minus t, and he put that integral of e to the minus t was e to the minus t. So pay attention to the sign. Remember that integral of e to the at dt is e to the at over a plus, right? Okay, so this is what you have, a minus plus C3. Pay attention also to the exams, because in the exams when you rush, you make lots of mistakes like that. R of 0 is given, so the initial position is given as C1, I'm replacing in my formula, it's going to be C1, C2, and what? When I replace the 0 here, what am I going to get? Minus 1, plus C3. Note that I fabricated this example so that C3 is not going to be 0. I wanted some constants to be 0 and some constants to not be 0, just to realize, for you to realize it's important to pay attention. Okay, minus 1 plus C3. And then I have 0, 0, 1 as given as initial position. So what do you get by solving this linear system? That's very simple. In general, you can get more complicated stuff. C1 is 0, C2 is 0, C3 is a 2, and so it was a piece of cake. What is my final answer? If you leave it like that, generally you don't get full credit. What would you need to do to get full credit?
RT is equal to arctan plus 1/2 sine 2t plus t cubed over 3 minus t.
Precisely, and thank you so much for your help. So you have arctan of t, 1/2 sine of 2t, and t cubed over 3 minus e to the minus t plus 2. I'm close, and that's it. And what's your answer? Right? So I got the law of motion back. Similarly, you could find, if somebody gives you the acceleration of a law of motion and asks you, this is the acceleration, and I give you some initial values, and you have to find first the velocity going backwards one step, and from the velocity backwards the second step, get the position vector. And that sounds a little bit more elaborate, but it doesn't have to be a long computation. In general, we do not focus on giving you an awfully long computation. We just want to test your understanding of the concepts. And having this in mind, I picked another example. I would like to see what that is, and the initial velocity will be given in this case. This is what I was thinking a little bit ahead of that. So somebody gives you the acceleration and the velocity vector at 0, and is asking you to find the velocity vector. So let me give it to you for t between 0 and 2 pi. I give you the acceleration vector, really nice and sassy. Let's see, that's going to be cosine of t, sine of t, and 0. And you say, oh, I know how to do those. Of course you know, but I want you to pay attention to the constants of integration. This is why I do this kind of exercise again. So what do we have for v of t? V of 0, somebody will say, let's give something nice, and let's say this would be, I have no idea what I want. Let's say I plus j, and that's it. How do you do that? V of t, let's integrate together. You don't like this? I hope that by now you got used to it. The bracket, angular brackets, okay, like in the book. So sine t plus a constant. What's integral of sine, guys? Negative cosine t plus a constant, and c3 as a constant. And there I go. You say, oh my God, what am I having? V of 0 is as a vector represented in the canonical standard basis as 1, 1, and 0. So from that one, you can jump to this one and say, yes, I'm going to plug in 0, see what I get. In the general formula, when you plug in 0, you get C1, what is cosine of 0? Minus 1 I have here, plus C2, and C3, that is always there. And then V of 0 is what I got here. V of 0 has to be compared to what your initial data was. So C1 is 1, C2 is 2, and C3 is 0. So let me replace it. I say the answer will be cosine t plus 1, sine t plus 2, and the constant 0. But then somebody who is really an experimental guy says, well,
You have it backwards. It's sine of t plus 1 and negative cosine of t plus 2.
oh yeah. Wait a minute. This is,
Yeah.
I miscopied looking up. So I have sine t, I was supposed to look. Yeah. Minus cosine t. I'm done. Okay. Too close. So, thank you for telling me. So, sine t plus 1 minus cosine t plus 2 and 0 are the functions that I put here by replacing c1, c2, c3. And then somebody says, wait a minute, now let me give you v of 0. Let me give you r of 0. V of 0 is already there. And you were supposed to get r from here. So what is r of t? The position vector. Find it. If v of t is given, actually is given by you because you found it at the previous step. And r of 0 is given as well. And let's say that would be, I don't know. Let's see, 1, 1, and 1. So what do you need to do next? You have r prime given. That leads you to integrating, you get r of t. And r of t is going to be what? Who is going to tell me what I have to write down? Minus cosine t plus t plus, let's use the word k1 this time, the constant k1 of integration. And then what?
Sine t.
I think it's minus sine, right? Minus sine t plus 2t plus k2 and k3, right? So r of 0 is going to be what? First of all, we use this piece of information. Second of all, we identify it from the formula we got. So from the formula I got, just plugging in 0, it should come out straight as minus 1 plus k1, 0 for this guy, 0 for the second term, k2, and k3. So, who is helping me solve the system really quickly? Kappa 1 is 2, kappa 2 is, kappa 3 is 1. And I'm going back to r of t and replace it, and that's my final answer for this two-step problem. So I have a two-step integration from the acceleration to the velocity, from the velocity to the position vector. Minus cosine t plus 2. Keep an eye on me because I have a tendency to miscopy. Am I looking in the right place? Yes. So I have minus sine t plus 2t plus 1, and kappa 3 is 1. All right, so this is the process you are supposed to remember for the rest of the semester. It's not a hard one. It's something that everybody should master. Is it hard? How many of you understood this? Please raise hands. Oh, no problem. Good. Very good. Now, could you tell me, I'm not going to ask you what kind of motion this is. It's a little bit close to a circular motion, but not a circular motion. However, can you tell me anything interesting about the type of trajectory that I have in terms of the acceleration vector? The acceleration vector is beautiful, just like in the case of the washer. That was a vector that, like, this would be the circular motion. The acceleration would be this unit vector that comes inside. Is this going outside or coming inside? Is it a unit vector? Yes, it is a unit vector. So suppose that I'm looking at the trajectory if it were more or less a motion that has to do with some, I don't know, mixing into a bowl. Would this go inside or outside? Towards the outside or towards the inside? I plus J depends on what I'm looking at in terms of surface that I'm on, right? Do you remember from last time we had that helix, but that was on a cylinder, and we asked ourselves, how is I plus J pointing? And it was pointing outside of the cylinder, right, in the direction towards the outside. All right, coming back to the review. There are several things I'd like to review, but not all of them, because some of the examples we have there, you understood them really well. I was very proud of you when I saw that you finished, almost all of you finished the homework number 1. So I was looking outside at homework number 2. That is over these 3 sections. So I was hoping you would ask me today between 2 and 3 if you have any difficulties with homework 2. That's due February 11th. And then the latest homework that I posted yesterday, I don't know how many of you logged in, but I just posted, last night I posted a homework that gave you a huge extended deadline, which is the 28th of February, considering that somebody's birthday is February 29th. I was just thinking, why would somebody need the whole month? You would need the whole month to have a good view of the whole chapter 11. I sent you the videos for chapter 11, and for chapter 11 you have this huge homework, which is 49 problems, I don't know. So please do not leave it to the last 5 days or 6 days, because it's gonna kill you. There are people who say, I can finish this in the next 5 days. I know you can. I know you can. I don't doubt it. That's why I left you so much freedom. But you have, today is the 2nd or the 3rd. So practically you have 25 days to work on this. And on the 28th at 11 p.m. is going to close. I would work a few problems every other day, because I need a break, right? So I would alternate. But don't leave it, even if you have help, and especially if you have help, like a tutor or tutoring services here that are free in the department. Do not leave it to the last days, because you're putting pressure on yourself, on your brain, on your tutor, on everybody. Yes, sir?
So that's homework 3?
That's homework 3, and it's a huge homework over chapter 11.
So there were 49 problems?
I don't remember exactly, but 47, 49, 40, I don't remember how many.
Between 45 to 50, right?
Between 45 and 50, yes. If you encounter any bug, although there shouldn't be bugs, maybe 1 in 1,000. If you encounter any bug that the programmer of those problems may have accidentally put in, you let me know, so I can contact them. And if there is a problem that I consider shouldn't be there, I will eliminate that later on. But hopefully it's going to be, everything will be doable, everything will be fair, and you will be able to solve the things. Okay. Any questions? Particular questions from the homework?
It's asking, it's telling us like parameterize a circle of radius, like over a certain radius in the XY plane.
Shall we do that? Do you want me to do that in general in XY plane? Okay.
The question is in the XY plane.
XY plane, and then what was the equation? Was it like A cosine of t or A cosine of bt? Because it's a little bit different depending on how the parameterization was given. What's your name again? I forgot. I don't know what to refer you.
Ryan.
Ryan. Okay.
Question number 5.
Was that part of what's due on the 11th?
It doesn't, yes, it doesn't give any equations. It
Okay,
says,
let me quickly read the find parameterization of the circle of radius 7 in the xy plane centered at 3, 1, oriented counterclockwise. The point 10, 1 should be, can I take this one second? Do you mind if I put it on? I'll take good care of it, I won't drop it. So, okay, so the point, parameterization of the circle of radius 7 in the xy plane centered at 3, 1. So, circle centered at, and I'll say it x0, y0 being 3, 1, okay? Because, no, because then that means I'm solving your problem. But I'm solving your problem anyway, even if I change the numbers. Why don't I change the numbers and then you do it for the given numbers? And let's say 1, 0. And it's the same type of problem, right? Oriented counterclockwise. That's important. With, so Ryan, you have circle radius 7. I think people could have any other, because problems are, sometimes you get a random assignment. So you have R equals 2, let's say. And you have the point, I'll make up something, the point corresponding to t equals 0 will be given as you have then 1, I 1, 1, 0, whatever, okay? Use the t as the parameter for all your answers. So use t as a parameter for all your answers, and the answers are written in the interactive field as x of t equals what and y of t equals what, and it's waiting for you to fill them in, you know that. Okay, now I was talking to Unitish, and so let me give this back to you. Thank you, Ryan. So when you said it's a little bit frustrating, and I agree with you, that in this variant of web work problems, you have to enter both of them correctly in order to say yes, correct. I would have liked, I was used to another library. The library was updated, this is the new library, where if I enter this correctly, I get 50% credit, and if I enter this incorrectly, it's not going to penalize me. So I a little bit complained about it, and I was shown the old library where I can go ahead and go back and assign problems where you get the answer correct for this one and incorrect for that one, and you get partial credit. So I'm probably going to switch to that. Guys, let's do that. This is a very good problem. I'm glad you brought it up. What have you learned about conics in high school? You've learned about, well, depends. You've learned about ellipse. You've learned about hyperbola. You've learned about parabola. Some of you put them down for me for extra credit. I was very happy you did that. It's a good exercise. If you have, Alex, yes?
I was just looking, does that say 1, 0? The point corresponding to T0
I think that's what I meant. I don't know. I just came up with it. I made it up. 1, 0. I make up all my
problems. The center of the
problems.
circle is at 1, 0.
Oh, oops. Yes.
So,
Sorry. So 2, 0. No.
Or the radius is 3, 0.
Because 3, 0 because the radius. This is the problem when you don't think very deeply. I always like to make up my own problems. When we came up with the problems in the book, of course we had to think, draw, and make sure they made sense. But when you just come up with a problem of the middle of nowhere that Thank you so much. Of
No
course,
problem.
we would have realized that was
Yeah.
nonsense in just a minute, but it's good that you told me. So, x of t, y of t. Let's find them. Based on what? What is the general equation of a circle? X minus x0 squared plus y minus y0 squared equals r squared. And you have learned that in high school. Am I right or not? You have. Okay, good. Now, in our case, what is x0 and what is y0? x0 is 1 and y0 is 0 because that's why I don't know, I just made it up. And I said that's the center. I'll draw. I should have drawn it in the beginning and that would have helped me not come up with some nonsensical data. C is 1, 0, radius is 2. So I'm going this way. What point is this way, guys? Just by the way. This is minus 1, 0, right? And this way, the other extreme, the antipode is 3, 0. So that's exactly what Alexander was saying, and now it makes sense. Well, I cannot draw today.
Ryan, is this number 5?
It looks horrible. It looks like an egg that is shaped, disabled egg. Okay. All right. So the motion will come like that. From t equals 0, where I'm here counterclockwise, I have to draw any kind of circle you have in the homework should be drawn on the board. Now, if you have a general, you don't know what the data is. I want to help you solve the general problem. For the general problem, which is a circle of center x0, y0, and radius r, generic one, what is the parametrization without data, okay? Without specific data. What is the parametrization? And I want you to pay attention. Very well, you are paying attention. You are very careful today. Yeah, I'm not. So what do you have?
Cosine.
Before the cosine, there is an r. Excellent. So they are both there. R cosine of t. I'm not done. What do I put here? No. I'm continuing.
Plus x0.
Plus x0. And r sine t plus y0. Who taught me that? First of all, this is not unique. It's not unique. I could put sine t here and cosine t here and it would be the same type of parametrization. But we usually put the cosine first because we look at the x-axis corresponding to the cosine and the y-axis corresponding to the sine. If I don't know that, because I happen to know that from when I was 16 in high school, if I don't know that, what do? I cook up my own parametrization, and that's a very good thing, and I'm glad Ryan asked about that. How does one come up with this? Do we have to memorize? In mathematics, thank God, we don't memorize much. The way we cook up things is just from, in this case, from the Pythagorean theorem of Pythagorean theorem of trigonometry. The fundamental identity of trigonometry, which is the same thing as the Pythagorean theorem, right? What's the fundamental identity of trigonometry? Cosine squared plus sine squared equals 1. If I have a problem like that, I must have that this is r cosine t, and this is r sine t, because when I take the red guys and I square them and I add them together, I'm going to have r squared. Alrighty, good. So, no matter what kind of data you have, you should be able to come up with this on your own. And what else is going to be happening? When I solve for x of the point corresponding to t equals 0, x of 0 and y of 0 will therefore be what? Will be r plus x0. This is going to be what? Just y0. Does anybody give them to me? Alexander gave me the correct ones. They will be 3 and 0. Are you guys with me? They could be anything. Anything that makes sense, of course. All right? For example, somebody would say, I'm starting here. I give you other points. Then you put them in, you plug in that initial point, meaning that you're starting your motion here, and you do go around the circle one time because you take only between 0 and 2 pi. Alexander.
No, I corrected myself.
Okay, all right. No, I thought that I misprinted something again.
No, I was about to say something really down.
Okay, all right. So how do we make sense of what we have here? Well, y0 corresponds to what I said. So this is a superfluous equation. I don't need that. What do I know from that? R will be 2, x1 is 1. I have a superfluous equation. I have to get identities in that case, right? Okay, now, what is going to be my bunch of equations will be x of t equals 2 cosine t plus one and y of t equals, I don't like this marker, I hate it. Where did I get it? In the math department, and it's a new one. I got it as a new one, it's not working. Okay, y of t. The blue contrast is more visible. I have 2 sine t. Okay, when you finish a problem, always quickly verify if what you got makes sense, and obviously, if I look at everything, it's matching the whole problem, right? Okay, now, going back to, which this is reminding me of something in 3D that I wanted to talk to you today about. This is very I'm going to give you, in a similar way with this simple problem, I'm going to give you something more complicated and say, find the parametrization of a helix, and you say, well, I'm happy with that. This isn't made up problem again. I have to be a little bit more careful with these made up problems so that they make sense. Of a helix R of t such that it is contained, or it lies on the circular cylinder x squared plus y squared equals 4. Why is that a cylinder? The z is missing, so it's going to be a cylinder whose main axis is the z-axis, right? Are you guys with me? I think we are on the same page. And you cannot solve the problem just with this data. Do you agree with me? Knowing that, the curvature of the helix is k equals 2/5 at every point. Of course, it's an oxymoron because what we proved last time is that the curvature of a helix is a constant. So remember, we got the curvature of a helix as being a constant.
What's the last word of the sentence? The curvature is at every what?
At every point. I'm sorry, I said it I abbreviated and I said every point. So at every point you have the same curvature. When you draw a helix, you say, wait, the helix is bent uniformly. If you were to play with a spring taken from an old bed, you would go with your hands along the spring. And then you say, oh, it bends about the same. Yes, it does. And that means the curvature is the same. How would you solve this problem? But this problem is hard because you cannot integrate the curvature. Well, what is the curvature? The curvature would be just absolute value of R double prime if it were in S. And you cannot integrate, if somebody gave you the vector equation R double prime of S, then you say, yes, I can integrate one step going back, I get R prime of S, then I go back to R of S, but this is a little bit complicated, I'm giving you a scalar. You have to be a little bit aware of what we did last time and try to remember what we did last time. What did we do last time? I would not give you a problem like that on the final because it would assume that you have solved the problem we did last time in terms of R of t equals A cosine t, A sine t and Vt, and we said this is the standard parametrized helix that sits on a cylinder of radius A and has the pitch B. So the distance between consecutive spires really matters. That B makes the difference. You wanted to ask me something.
Is S always a reciprocal of t? Like, are they always like?
No, not reciprocal. You mean S of t is a function that is from t0 to t of the speed. R prime of t, d tau, right? Tau not t. The dummy variable. T and S are different parameters, right? Different times, different parameter types. And you say, is it the
parameter time when it's at Arcline parameter as?
Very good. So what is the magic S? I'm proud of you. This is the most important thing to remember. T could be any time. I start measuring wherever I want. I can set my watch to start now. It could be crazy. It doesn't have to be a uniform motion. I don't care. S is a friend of yours that says, I am that special time so that according to me, the speed will become 1. So for a physicist who measures the speed with respect to this parameter S time, the speed will always become 1. That is the arc length parameterization. How you get from one another, I told you last time that for both of them you have, this is R of t and this is a little R of S, and there is a composition. S can be viewed as a function of t, and t can be viewed as a function of S. As functions, they are inverse to one another. So going back to who they are very good question because this is review anyway. Who was S as a function of t for this particular problem? I hope you remember. We were like, have you seen this old movie with Mickey Mouse going on, it was like a mountain that was more like a cylinder, and this is the train going at a constant slope, and one of my colleagues, actually he's at Stanford, was telling me that he gave his students in Calc 1 to formally prove that the angle formed by the law of motion by the velocity vector with the horizontal plane passing through the particle is always a constant. I didn't think about doing it now, but of course we can. We could do that. So maybe the next thing would be like, if it were an extra problem, can we show that angle between the velocity vector along the helix and the plane, horizontal plane through that point is a constant.
Isn't it just because b of t is just a constant times t?
Yeah, then we'll get to that. We'll get to that in a second. So he reminded me of an old movie from like 70 years ago with Mickey Mouse in the train, and the train going at the same speed. And you have to maintain the same speed, because if you risk it not, then you sort of get in trouble. So you never stop. If you stop, you go back. So it's a regular curve. What I have here is that such a curve. Regular curve, never stop, get up with a constant speed. Do you guys remember the speed from last time? Was square root of a squared plus b squared, when we did the velocity thingy, and I get square root of a squared plus b squared times t. Now, today I would like to ask you one question. What if, when Ryan brought this up, it's very good, b is a constant. What if b would not be a constant, or maybe could be worse? For example, instead of having not a linear function bt, but something that contains higher powers of t. Then you don't go at the constant speed anymore. Goodbye this. You can say goodbye to the cartoon. Yes, sir?
And then it's no longer a helix.
Uh,
One that goes at the same.
I mean, it's still.
S is not multiplied by a constant anymore. The
S
function between
is,
t and s
it's
is not a, it's not a
gonna
constant.
be a different parameterization, different speed. Sometimes okay, you have to understand. Let's say I have a cone, and I'm going slow at first, and I go faster and faster and faster and faster and faster to the end of the cone. But then I have the same physical curve, and I parameterize in arc length, and I say, no, I'm a mechanic, I'm the engineer of this train, I can make the motion have a constant speed. So even if the helix is no longer circular and is sort of a crazy helix going on top of the mountain, as an engineer, I can just say, oh no, I want cruise control for my little train, and I will go at the same speed. See, the problem is the slope a constant? And thinking of what they did at Stanford, if they did at Stanford in honors, we can do it in honors here as well. We'll do it in a second. Now, K obviously is what? Some of you have very good memory, and like the memory of a medical doctor, which is great. Some of you don't. But if you don't, you just go back and look at the notes. What I'm trying to do, but I don't know, it's also a matter of money. I don't want to use the math department copier. I'd like to make a stack of notes. So that's why I am collecting these notes, to bring them back to you for free. I'm not going to sell them to you. I'm against this idea. So that you can have those with you whenever you want, or put them in a spiral, punch holes in them and have them for review at any time. Who reminds me what that was? That was in the notes, a over a squared plus b squared. So who can tell me a and b really quickly so we don't waste too much time? Mr. A is
So this is another way of saying
Two.
k of A.
2.
So is this another way of defining k? The k of s?
Actually,
That's the general curvature for a helix.
you know what is the magic thing? Even if the curvature is an invariant, it doesn't depend on the reparametrization. There is a way, maybe I'm going to teach you, although this is not in the book. What are the formulas corresponding to the Frenet trihedron T and V that is depend on curvature and torsion and the speed along the curve? And if you analyze the notion of curvature, it's good that you asked, no matter what your parameter will be, T, S, tau, God knows what, K will still be the same number. So K is viewed as an invariant with respect to the parametrization.
So
So,
then that A over A squared plus B squared, that's another way of finding K.
say it again.
So using A over A squared plus B squared is another way of finding K.
No, somebody gave you K, and then you say if it's a standard parametrization, and then I get 2 over 5, can I be sure A is 2?
Yes.
I'm sure A is 2 from that. This is what makes me aware that A is 2 in the first place, because it's the radius of the cylinder. This is x squared, x and 1. You see x squared plus y squared is a squared. This is where I get A from. A is 2. I replace it in here and I say, oh, righty, so I only have one choice. A is 2 and B is
Or negative 1.
What?
One is square root of 1. That's negative 1.
but can be plus.
But it's going upwards.
So what I'm saying, A is 2, right? We know from that, from this. If I plug in here, I have 4, and somebody says plus minus 1. No, B is always positive. So you remember last time we discussed about the standard parametrization. But somebody will say, but what if I put a minus? What if I'm going to put a minus? That's an excellent question. What's going to happen if you put minus t?
You gotta hit a strong.
Exactly, in the opposite direction. You go, instead of going up, you go down. All right. Now, I'm gonna, what else? I said, let's do this. Let's prove that the angle is a constant. The angle that's made by the velocity vector of the train with the horizontal plane is a constant. Is this hard? Nah, yes sir.
Are we still going to find R of t given only k?
But isn't we did. R of t was 2 cosine t, 2 sine t, and t. All right?
Okay.
Okay, so we are done. What did I say? I said that let's prove, it's a proof. Let's prove that the angle made by the velocity to the direction of motion, which is the helix, and the horizontal plane is constant. Is this hard? How are we going to do that? Now I start waking up because I was very tired. Excuse me.
Change of mind to that function.
So you see, the helix contains this point, and I'm looking at the velocity vector that is tangent to the helix, and I'll call that r prime. And then you say, yeah, but how am I going to compute that angle? What is that angle?
Well, it's a function of b.
It will be, but we have to do it rigorously. So what's going to happen for me to draw that angle? First of all, I should take from the tip of the vector, I should draw perpendicular to the horizontal plane passing to the point. And I get P prime, God knows why, I don't know what else. Q. And this is PR and P, not PR. PR is too much confounded with radius, M. Okay, so then you would take PQ and then you would measure this angle. Well, you have to be a little bit smarter than that because you can prove something else. This is the complement of another angle that you love, and using chapter 9 you can do that angle in no time. So this is the complement of the angle formed by the velocity vector r prime with the normal. But not the normal, principal normal to the curve, but the normal to the plane. And what is the normal to the plane? Let's call the principal normal n to the curve big N bar. So in order to avoid confusion, I'll write this little n. How about that? Do you guys want to know? Like they do in mechanics. If you have two normals, they call that one n, one is little n, and stuff like that. So this is the complement. If I were able to prove that that complement is a constant, this is the Stanford problem, then I will be happy. Is it hard? No, for God's sake. Who is little n? Little n would be, is that the normal to a plane that you love? What is your plane? Your plane is horizontal plane. Yes, xy plane. Or xy plane shifted, 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 shifted. Does the normal change? No. Who is the normal? Wait. 0, 0, 1. Okay, when I heard 0, I was about to faint. So this is K. All right. And what is our prime? The velocity. That was a piece of cake. We did it last time. Minus a sine t, a cosine t, and b. Let's find that angle. Well, I don't know. You have to teach me because you have chapter 9 fresher in your memory than I have it. Are you taking attendance also? Are you writing your name down? Oh, no problem whatsoever.
We didn't get it.
You didn't get it, you circulated. All right, so who is going to help me with the angle? What is the angle between two vectors, guys? That should be reviewed from what we just covered in chapter 9. Let me call them U and V. And who's going to tell me how I get that angle?
Theta is equal to the inverse cosine of the dot product of the magnitudes.
Do you like me to write arc cosine or cosine inverse? Doesn't matter. Arc cosine of
the dot
product between U and V divided by the product of their magnitudes. Well, I won't change it in order because you're not going to like it. Doesn't matter. Okay? So, the angle phi between my favorite vectors here is going to be simply the dot product. That's a blessing. It's a constant.
So you're doing the dot product between the normal and
between this and that. So this is U and this is V. So the dot product will be 0 plus B. So the dot product is arc cosine of B, which thank God is a constant. I don't have to do anything anymore. I'm done with the proof because arc cosine of a constant will be a constant. Okay? All right. So I have D over what? What is the length of this vector? 1 is a unit vector. What's the length of that vector? Square root of a squared plus b squared. All right?
How did you go to B? Oh, okay.
All right. So now let me ask you one thing. What kind of function is arc cosine? Of course, I said arc cosine of a constant is a constant. What kind of a function is arc cosine? I'm doing review with you because I think it's useful. Arc cosine is defined on what with values in what?
So repeat the question.
Repeat the question. Arc cosine, or cosine inverse, like Ryan prefers cosine inverse, it's the same thing. Is a function defined from where to where? Cosine is defined from where to where? From R to minus 1. It's a cosine of t. T could be any real number. The range is minus 1, 1.
Okay,
Close the interval.
So it's minus 1 to 1.
Minus 1 to 1, close the interval. But pay attention, please, because it cannot go back to R. It has to be a 1-to-1 function. You cannot have an inverse function if you don't take a restriction of a function to be 1-to-1. And we took that restriction of a function, and do you remember what it was?
It goes at 0 to pi.
0 to pi, excellent. Now, on this one, I'm really happy because I've asked several people come to my office to get all sorts of transcripts looked at, and in trigonometry I asked one student, so you took trigonometry, so do you remember that? He didn't remember that. So I'm glad you do. How about when I had a sine inverse?
There we go.
How was my restriction so that would be a 1-to-1 function? It's going to go from minus 1 to 1. What is the range?
Negative pi over 2.
Minus pi over 2. You guys know your trick. Oh, good. That's a very good thing. You were in high school when you, right? When you learned that?
Yeah.
Here, Lubbock High? Okay, good job, Lubbock High. But many students, I caught them who wanted credit for trick who didn't know that. Good. So since arc cosine is a function that is on 0 pi, for example, what if my, let me give you an example. What was last time, guys? A was 1, B was 1, one examples. In that case, what would phi be?
Are you asking for the example we just did?
No, last time.
A was 3 and B was 4.
So what would that be in this case, phi?
That would be B over the square root.
3 over 5.
Huh? A is 1 and B is 1, like we did last
That would
time.
be the square root of 2 over 2, which is this.
Plug in, 1 is A, B is 1, what
Which
is
pi over
this?
4.
Pi over 4, so pi will be arc cosine of 1 over square root 2, which is 45-degree angle, which is pi. You said pi over 4, right? You said it, okay. All right, so exactly you would have that over here. This is where the cosine is positive. Now you see, guys, the way I assumed A and B, the way the book also introduces A and B to be positive numbers. Can you tell me what kind of angle phi will be, not only restricted to 0 pi? Well, A is positive, B is positive, A doesn't matter. The whole thing will be positive. Arc cosine of a positive number,
Between 0 and power 2.
that is, yeah, so it has to be between 0 and power 2. So it's going to be only this quadrant. Does that make sense? Yes, think with the imagination of your eyes, or the eyes of your imagination. Okay, you have a cylinder, and you are moving along that cylinder, and this is how you turn. You turn with that little train. You go up. When you turn the velocity vector and you look at the normal, thank you, the z-axis, you always have an angle between 0 and pi over 2. So it makes sense. I'm going to go ahead and erase the whole thing. So we reviewed, more or less, S of t, integration, derivation, moving from position vector to velocity to acceleration and back, acceleration to velocity to position vector, the meaning of arc length. There are some things I would like to tell you because Ryan asked me a few questions, more questions about the curvature. The curvature formula depends very much on the type of formula you used for the curve. So you say, wait, Magdalena, you told us, you were confusing us. You told us that the curvature is uniquely defined as the magnitude of the acceleration vector when the law of motion is in arc length. And that is correct. So suppose my original law of motion was r of t, a wild time, any time t, any time parameter. I'm making a face. But then, from that we switch to something beautiful, which is called the arc length parametrization. Why am I so happy? Because in this parametrization, the magnitude of the speed is 1. And I define k to be, the magnitude of r double prime of s, right? The acceleration only in the arc length parametrization, and this was the definition. A. Can you prove what? Can you prove the following formula? T prime of S equals K times N of S. This is famous for people who do, not for everybody, but imagine you have an engineer who does research of the laws of motion. Maybe he works for the railways and he's looking at skew curves, or he is one of those people who project the ski slopes or all sorts of winter sports slope or something that involve a lot of curvatures and torsions. That guy has to know the Frenet formula. So this is the famous first Frenet formula. Frenet was the mathematician who gave the name to the T and B vectors, the trihedron. You have the T was what? The T was the tangent unit vector. The N was the principal unit normal. In those videos that I'm watching that I also sent you, I like most of them. I like the Khan Academy more than everything. I like the one that was made by Dr. Bob. Okay, but Dr. Bob made a little bit of mistake. I mean, conceptual mistake. We all make mistakes by misprinting or misreading or goofy mistake. But he said this is the normal vector. This is not. It's a principal normal vectors. There are many normals. There is only one tangent direction, but in terms of normals, there are many. All of these are normals. All the perpendicular in the plane, I'm coming towards you, so this is my law of motion, T. All this plane is normal. So any of these vectors is a normal. The one we choose and define as T prime over T prime in absolute value is called the principal normal. It's like the principal of a high school. It's important. So Tn and B goes down or up? Goes down. Well, yeah, because B is T cross N. So we define the Frenet trihedron T and B. It's like that. T, N, and B. What's special, why do we call it a frame, is that every pair of vectors are mutually orthogonal. And they are all unit vectors. This is the famous Frenet frame. Now, Mr. Frenet was a smart guy. He found, I don't know whether he was a doctor in mathematics or not. It doesn't matter. He found a bunch of formulas, of which this is the first one, and it's called the first Frenet formula. That's one thing I want to ask you. And then I'm going to give you more formulas for curvatures, depending on how you define your curve. So, for example, based on the definition, one can prove that for a curve that is not parametrized in arc length, you say, forget about parametrization in arc length, it's time consuming. I want to know, and I'm coming to this because Ryan asked, I want to know what is the formula directly. Is there a direct formula that comes from here for the curvature? Yeah, but it's a lot more complicated. I was a freshman, maybe a freshman or a sophomore, I don't remember. When I was asked to memorize that, I did not memorize it. And then when I started working as a faculty member, I saw that I was supposed to ask it from my students. So this is going to be R prime cross product R double prime in magnitude over R prime cubed. So how am I supposed to remember that? It's not so easy. Are you cold there? It's cold there. I don't know how these rooms are made. Velocity times acceleration. This is what I try to teach myself. I was old already, about 26 or 27. Velocity times acceleration, cross product, take the magnitude, divide by the speed cube. Oh my God. So I was supposed to know that when I was 18 or 19. Now I was teaching majors of mechanical engineering. They knew that by heart. I didn't. So I had to learn. So if one is too lazy, or it's simply inconvenient to try to reparameterize from R of t in arc length parametrization RFS and do that thing here, one can just plug in and find the curvature like that. For example, guys, as Ryan asked, if I have a cosine t, a sin t, bt, and I do this with respect to t, can I get k without? K will not depend on t or s or tau, or it will always be the same. I will still get a over a squared plus b squared no matter what. So even if I use this formula for my helix, I'm going to get the same thing. I'll get a over a squared plus b squared because curvature is an invariant. There is another invariant that's the other invariant of curves in space called torsion. I'm going to talk a little bit about that later. So, is this hard? No, it shouldn't be hard, and you guys should be able to help me on that, hopefully. How do we prove that?
Well, n is t prime over magnitude
That's right, proof, and that's a very good start, what you're saying. So what were the definitions? Let me start from the definition of t. That's going to be, I am in arc length, right? So you say, wait, why do you write it as a quotient? You're being silly. You are in arc length, Magdalena. I am. I just pretend that I cannot see that. So if I'm in arc length, that means that the denominator is 1. So I'm being silly. So R prime of S is t. Say it again. R prime of S is t. Okay. Now, did we know that t and n are orthogonal? How did we know that t and n were orthogonal? We proved that last time, actually. T and n are orthogonal. How do I write that? In dot product. So meaning that t is perpendicular to n, right? From the definition. But why is, you said it right, Sandra, but why is it from the definition that I can jump to conclusion and say, oh, since I have t prime here, that means it's perpendicular to t? Well, we did that last time.
two parallel vectors.
We did it, how did we do it? We did it fast. We said t dot t equals 1, prime the whole thing, t prime times t plus t times t prime. T dot t prime will be 0, so t and t prime are perpendicular always, right? Okay, so the whole thing is a collinear vector to t prime. It's just t prime times a scalar, so he must be perpendicular to t. So t and n are perpendicular. All right, so I do have the direction of motion. I know that I must have some scalar here. How do I prove that this scalar is the curvature? So if I have, if they are collinear, why are they collinear? T perpendicular to t prime implies that t prime is collinear to n. Say it again. If t and t prime are perpendicular to one another, that means t prime is collinear to the normal. So here I may have alpha. I don't know. Alpha of s sounds like a curve. Give me some function.
U of S?
Gamma of s, mu of s, I don't know. So how did I conclude that? From t perpendicular to t prime. Now from here on, you have to tell me why gamma must be exactly kappa. Well, let's take t prime from here. T prime from here will give me what? T prime is r prime prime. Say what? R prime prime. What is r prime prime? R double prime of s.
You have one too many primes inside.
Oh my god, yeah.
Don't.
Thank you. So r prime prime. So t prime in absolute value will be exactly double prime novice. Oh, okay. Note that from here also, t prime novice in absolute value, in magnitude, I'm sorry, has to be gamma of s. Why is that? Because the magnitude of n is 1. N is unit vector by definition. So these two guys have to coincide. So r double prime of s in magnitude must coincide with the scalar gamma of s. So who is the mysterious gamma of s? He has no chance but being this guy. But this guy has a name. This guy is the curvature kappa of s by definition, DEF. Remember, Ryan, this is DEF definition. So by definition, the curvature was the magnitude of the acceleration in arc length. Okay, both of these guys are t prime in magnitude, so they must be equal. From here and here, it implies that my gamma must be kappa. And I proved the formula. Okay, how do you say something is proved? Because this is what we wanted. We wanted to replace this generic scalar function, prove that this is just a curvature. QED. QED. That's exactly what we wanted to prove. Now, whatever scalar function you have here, that must be the curvature. Very smart guy, this Mr. Frenet. I'm not going to take a break. If you want to go use the bathroom really quickly, feel free to do it. I'm just going to clean the board and I'll keep going in a few minutes. I want to do a different example, simple one, which is a plane curve, and show that the curvature has a very pretty formula that you could even memorize. That in essence is the same, but it depends on y equals f of x for a planar curve. So if somebody gives you a plane curve y equals f of x, can you write that curvature directly as a function of f? And you can. And again, I was given that when I was 18 or 19 as a freshman, but unfortunately for me, I didn't learn it at that time. And several years later, when I started teaching engineers, well, they were mostly mechanical engineers were most of the majors. They knew those and they needed those in every research paper, so I had to learn it together with them. I'll work on a little bit curvature, one or two more. I can do some ugly ones as well.
We started off strong. Oh my God, Super Bowl. Blake lost it. And I knew he lost it. They gave me the screen. And then James involved in this.
And once you know that general parametrization will give you a curvature. Now I'm testing your memory. Let's see what you remember. Don't look at the notes. A positive function, absolute, actually magnitude of what vector? R prime velocity cross acceleration. Speed cubed, right? Okay, now, can we take advantage of what we just learned and you find with me, of course, not as professor and student, but like a group of students together. Let's find a simpler formula corresponding to the curvature of a plane curve. And the plane curve could be given in two different ways, just because I want you to practice more on that. Either given as a general parametrization. Guys, what is the general parameterization I'm talking about for a plane curve? X of t, y of t, right? X equals x of t, y equals y of t. So one should not have to do that all the time. I mean, not have to do that for a simplification like a plane curve. We have to find another formula that is pretty, right? Well, maybe it's not as pretty, but let's see, when is it really pretty? I bet it's going to be really pretty if you have a plane curve given as you're used to in an explicit form. I keep going. No, stop. I mean, or no. I think it's better. We make better use of time this way. Or y equals f of x. This is an explicit way to write the equation of a curve. Okay, so what do we need to do? That should be really easy. R of t. In the first case of a general parametrization, x equals x of t, y equals y of t, will be, who tells me, guys, that this is in your hands. Now you convinced me that for whatever reason you mastered it. You became friends with these curves. I don't know when. I guess in the process of doing homework. Am I right? I think you did not quite like them before or last week, but I think you're friends with them now. X of t, y of t, and let people talk. Zero. Great. And then r prime of t will be x prime of t, y prime of t, and 0. I assume this to be always non-zero. I have a regular curve. R double prime will be x double prime, y double prime. We did the review today of velocity and acceleration. Now, your friends over here, are they nice or mean? I hope they are not so mean. The cross product is a friendly fellow. You have ijk, and then the second row would be x prime, y prime 0. The last row would be x double prime, y double prime, 0, and it's a piece of cake. But, okay, piece of cake, but I want to know what the answer is. So you have exactly 15 seconds to answer this question. Who is R prime cross R double prime as a formula?
Prime y double prime minus y.
Good. X prime y double prime minus x double prime y prime
K.
times k. And it doesn't matter when I take the magnitude because magnitude of k is 1. So I discovered something. This is how mathematicians like to discover new formulas based on formulas they are given. They have a lot of satisfaction. Look what I got. Of course, they in general have more complicated things to do, and they have to check and recheck. But every piece of a computation is a challenge, and that gives people satisfaction. And when they make a mistake, it brings a lot of tears as well. So, what's to be written on the bottom? What's the speed cubed? Speed is coming from this guy. So the speed of the velocity, the magnitude of the velocity is the speed. And that I'm going to give you a square. I'm not going to write down jump on square root of x squared, x prime squared plus y prime squared, and I cube that. Many people, when I saw that in engineering, they don't like to put that square root anymore, and they just write x prime squared plus y prime squared to the what power? 3 halves. So this is very useful for engineering studies when you have to deal with plane curves, plane motions in plane curves. But now, what do you have in the case, in the happy case, when you have y equals f of x? I'm going to do that in a second. I want to keep this formula on the board. What's the simplest parametrization? Because that's why we needed to look over parametrizations again and again. R of t for this plane curve will be, what is t? X is t, right? X is t, y is f of t, so piece of cake, so you have t and f of t. And how many of you watched the videos that I sent you? Do you prefer Khan Academy or you prefer the guys who are lecturing, the professors who are lecturing in front of a board or in front of a, what is that, the projector screen? I don't know. I like all of them. I think they're very good. I think you can learn a lot from 3 or 4 different instructors at the same time. That's ideal. Well, I guess that you have this chance only now in the past few years, because 20 years ago, if you didn't like your instructor or just you couldn't stand them, you had no other chance. There was no YouTube, no internet, no way to learn from others. R prime of t will be 1 f prime of t, but instead of t I'll put x because x is t, I don't care. R double prime of t will be 0 f double prime of x. So I feel that, hey, I know what's going to come up, and I'm ready, well, we are ready to write it down. This is going to be Mr. x prime, this is going to be replacing Mr. y prime, this is going to replace Mr. x double prime, this is going to be replacing Mr. y double prime of x. Oh, okay, all right, so K, our old friend from here, will become what? And I better shut up because I'm talking too much. That is the absolute value. F double prime of x and nothing else. Right, guys, are you with me? Divided by, shall I write square root? I love square roots. I'm crazy about them. So you go 1 plus f prime squared cubed. So that's gonna be, any questions? That's gonna, are you guys with me? That's gonna be the formula that I'm gonna use in the next example. In case somebody wants to know, oh, I got this question from one of you. Suppose we get the parameterization of a circle in the midterm or the final. Somebody says, I have x of t, just like we did it today, a cosine t plus x0, and y of t equals a sine t plus y0. What is this, guys? This is a circle, a center, x0, y0, and radius a. Can we use a better formula, well, that anticipated my action today, to actually prove that k is going to be 1 over a precisely? Can we do that in the exam? Yes. So well, I told you a long time ago that engineers and mathematicians observed hundreds of years ago. Actually, somebody said, no, you're not right. The Egyptians already saw that. They had the notion of inverse proportionality in Egypt, which makes sense if you look at the pyramids. So one look at the radius and says if radius is 2, then the curvature is not very bent, so the curvature is inverse proportional to the radius. So if this is 2, we said the curvature is 1/2. If you take a big circle, the radius, the bigger the radius, the smaller the bending of the arc of the circle, so the smaller the curvature. Apparently the ancient world knew that already, the Egyptians knew that, the Greeks knew that, but I think they never formalized it, not that I know. So if you were asked to do this in any exam, do you think that would be a problem? Of course we would do review, because people are going to forget this formula or even the definition. You can compute k from this formula and you're going to get k to be 1 over a. This is a piece of cake, actually. You may not believe me, but once you plug in the equations, it's very easy to compute. Or you can do it from the definition that gives you k of s. You reparameterize this in arc length. You can do that as well, and you still get 1 over a. The question that I got by email, and I get a lot of email, I told you, like, that keeps me about 200 emails every day. But I really like the emails I get from students, because I get emails from all sorts of sources. Lots of spam also, anyway. So what I'm trying to say, I got this question last time, saying if on the midterm we get such a question, and we say simply, curvature is 1 over a is the radius, is that enough? Depends on how the problem is formulated. Most likely I'm going to make it prove that or show that. Even if you state something like, yes, it's 1 over a, with a little argument, it's inverse proportional to the radius, I will still give partial credit. For any argument that is valid, especially if it's based on empirical observation, I do give some extra credit, even if you didn't use the specific formula. Let's see one example. Let's take y equals e to the x. No, let's take e to the negative x. Doesn't matter. Y equals e to the negative x. And let's take x between 0 and 1. And say, write the curvature, write the equation or the formula of the curvature And I know it's 2 o'clock and I am answering questions. This was a question that one of you had during the short break we took. Can we do such a problem? Like she said e to the x, I say e to the negative x because I don't know. I want to catch somebody not knowing the derivative. I don't know why I'm doing this, right? So if I were to draw that, okay, try and draw them, but not now. Now, what formula are you going to use? Of course, you could do this in many ways. All those formulas are equivalent for the curvature. What's the simplest way to do it? Do y prime minus e to the minus x. Note here in this problem that even if you mess up and forget the minus sign, you still get the final answer correctly. But I may subtract a few points if I see something nonsensical. Y double prime equals plus e to the minus x. And what is the curvature k of t?
Y prime over.
Oh, I didn't say one more thing. I want the curvature, but I also want the curvature in 3 separate moments.
Wait.
In the beginning, in the end, and in the middle. Yes, sir.
Do you need to parameterize it so you can bring it into x prime, y prime? Break it out?
No, you see, did I erase it?
Yeah, you did.
Guys, I'm something terrible. And one of my colleagues said, Magda, you are smart, but you're like one of those people who gets out of, in the anecdotes about math professors, gets out of their office and starts walking and stops the student. Was I going this way or that way? And that's me, and I'm sorry about that. I should not have erased it.
Oh,
It was bad.
So we're using the
I'm going to go ahead and rewrite it because I'm a goofball.
Oh, okay. That's one of them.
So the one that I want you to use, k of x will be f double prime in
Cube.
so that cube. I got it. Thank you. Okay. So that 3/2, remember it. You can use the 3/2 or you can use square root cube. Now for this one, is it hard? No. That's a piece of cake. I said I like it in general, but I also like it. Find the curvature of this curve in the beginning. You travel on it from time 0 to 1 o'clock, whatever. 1 second. Let's say this is in seconds to make it more physical. I want the k at 0, I want k at 1/2, and I want k at 1. And I'd like you to compare those values. And I'll give you one more task after that, but let me start working. So you said you helped me on that. You don't wanna. The minus x over square root of 1 plus. Right, so can I write this differently, a little bit differently, like what? I don't want to square e to the minus 2x. Can I do that? And then the whole thing, I can say to the 3/2, or I can use the square root, whichever is your favorite. Now, what is k of 0?
0 or 1.
1 over.
Really?
1 over 2. 3/2.
So let's take it slowly because we can all make mistakes, goofy mistakes. That doesn't mean we're not smart. We're very smart, right? But it's just a matter of bookkeeping and being careful, being attentive, very paying attention, being attentive. Okay. When I take 0 and replace, this is drying, it has some time to dry. I have 1 over 1 plus 1 to the 3/2. So don't let, I had a student in one exam who was just, I don't know, he was rushing. He didn't realize that he had to take it slowly. He was extremely smart. 1 over,
2 square root 2.
you have the 1 plus 1 is 2. 2 to the 1/2 would be square root of 2 cubed, would be exactly 2 square root of 2. And more, you can write this as rationalized. Now, I have a question for you, square root 2 over 4. When we were kids, if you remember, but you're too young, maybe you don't remember, but I remember when I was a kid, my teacher always asked me, rationalize your answer, rationalize your answer. Put a rational number in the denominator. Why do you think that was? For hundreds of years, people did that. In school.
Divide by square root.
Because of they didn't have a calculator, right? So I used to be able to get the square root out by hand. Has anybody taught you how to compute square root by hand? You know that. Who
No,
taught you?
I don't remember it when my 7th grade teacher taught us.
There is a technique of taking groups of twos and then fitting them, and they still teach that. I was amazed. They still teach that in half of the Asian countries. And it's hard, but kids in 5th and 6th grade have that practice, which, I mean, some of us learned and forgot about. So imagine that how people would have done this. Of course, it's for 2, square root of 2 is easy. 1.4142, blah, 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 divide by 2, you can do it by hand. At least a good approximation. But imagine having a nasty square root there to compute, and then you divide by that natural number. So you have to rely on your own computation to do it. There were no calculators. How about k of 1? How is that? What is that? E to the minus 1. That's a little bit harder to compute, right? 1 plus e to the, what is that going to be? Minus 2. Replace x by 1 to the 3 halves. I would like you to compare, I would like you to go home and do the following. Compare, not now, we stay a little bit longer together. K of 0, K of 1/2, and K of 1. Which one is bigger? And one last question about that. How much extra credit should I give you? 1 point, 1 point, 1 point, if you turn this in. Yeah, 4, maybe 2 points. Compare all these 3 values and find the maximum and the minimum of kappa of t, kappa of x, for the interval where x is the interval, is in the interval 0, 1, 0, closed, 1, closed, closed it. Now, of course, don't ask me because it's extra credit. One question was by email, can I ask my tutor to help me? As long as your tutor doesn't write down your solution, you're in good shape. Your tutor should help you understand some concepts, spend time with you, but they should not write your assignment themselves. Okay? So it's not a big deal. All right, and now I want to tell you one secret that I normally don't tell my Calculus 3 students, but the more I get to know you, the more I realize that you are worth me telling you about that.
We don't erase it yet.
No. There is a beautiful theory that engineers use when they study motions of curves and parametrizations in space, and that includes the Frenet formulas. And you already know the first one, and I was debating, I was just reviewing what I taught you, and I was happy with what I taught you, and I said, they know about position vector, they know about velocity, acceleration, they know how to get back and forth from one another, they know arc length, they know how to reparameterize in arc length, they know the Frenet trihedron Tn and B, they know already the first Frenet formula, and they know the curvature. What else can I teach them? I want to show you. One of you asked me, is this all that we should know? This is all that a regular student should know in Calculus 3, but there is more, and you are honor students, and I want to show you some beautiful equations here. So do you remember that if I introduced R of S as a curve in arc length that is a regular curve, I said there is a certain famous formula that is T prime of S called leave space. Leave a little bit of space. You'll say, why? It's a surprise. K times, why don't I say K of S? Because exactly because I want to point out that K is an invariant, even if you had another parameter which would be the same function. But yes, as a function of S would be K of S. Times N bar bar. Or bars because they are free vectors. They are not bound to a certain point. They are not married to a certain point. They are free to shift by parallelism in space. However, I'm going to view them as bound at the point where they are. So they, in a way, they are married to the point that they belong to. Maybe maybe the n will change. I don't know how it's going to change like crazy. Something like that. At every point you have a t, an n, and it's a 90-degree angle. Then you have the binormal, which makes a 90-degree angle with each t and n. So guys, the way you should imagine these corners would be something like that, right? 90, 90, 90. It's just hard to draw them between the vectors you have here. If it were t and n, am I right that it's coming out? No, I have to switch them. T and n. Now, am I right? I'm thinking of the faucet. If I move t, yeah, now it's coming out. So this is because not getting into the board, right? Okay. So this is the first formula. I say, so what? You've thought that, we proved it together. What do you want from us? I want to teach you two more formulas. N prime. And I'd like you to leave more space here. So you have like an empty field here and an empty field here, nothing there. If you were to compute T prime, the magic thing is that T prime is also, T prime is a vector, N prime is a vector, B prime is a vector. They are all vectors. They are the derivatives of the vectors T and NB. And you say, why would I care about the derivatives of the vectors T and NB? I'll tell you in a second. So if you were to compute N prime, you're going to get here minus K of S times T of S. Leave room. Leave room because there is no component that depends on N. No such component that depends on N. This is in T. There is nothing in N. And then in the end you say plus tau of S times B. So there is something missing. And finally, if you take B prime, there is nothing here, nothing here. In the middle, you have minus tau of S times N of S. And now you know that nobody else but you know that. I mean, the other regular sections don't know these formulas. What do you observe about this bunch of equations? Say, oh, wait a minute. First of all, why did you put it like that? It looks like a cross. It is a cross. It is like one is shaped in the name of the Father, the Son, and so on. So, does it have anything to do with religion? No. But it's going to help you memorize better the equations. These are the famous Frenet equations. You only saw the first one. What do they represent? If somebody asks you what is K, what is K of S? What's the curvature? You go to a party, there are only nerds. It's you, some people taking advanced calculus, some people from physics, and they say, okay, have you heard of the Frenet motion, Frenet formulas? And you say, I know everything about it. But if they ask you, what is the curvature K? You say, curvature measures how a curve is bent when you... And they say, yeah, but the Frenet formula tells you more about that. Not only K shows you how bent a curve is, but K is a measure of how fast T changes. And he sees why. Practically, if you take the magnitude of that, this is how the speed of T. So how fast the T will change, that will be magnitude, will be just K, because magnitude of n is 1. So note that K of S is the length of T prime. This measures the change in T. So how fast T varies. Okay? What does the torsion represent? Well, how fast the binormal varies. But if you were to think of a helix, and this is a little bit hard to imagine, the curvature measures how bent a certain curve is. And it measures how bent a plane curve is. For example, for the circle you have radius A, 1 over A, and so on. But there must be also a function that shows you how a curve twists, because you have not just the plane curves where you care about curvature only, but in the space curve you care how the curves twist. How fast do they move away from a certain plane? Now, if I were to draw, so is it hard to memorize these? No, I memorize them easily based on the fact that everything looks like a decomposition. A decomposition of a vector in terms of T, N, and B. So in my mind, it was like I take any vector I want, V, and this is T, this is N, and this is B, just the way it was I, J, K. Instead of I have T, instead of J, I have N, instead of K, I have B. They are still unit vectors. So locally at the point I have of this frame, and I have any vector. This vector, I'm a physicist. So let's say I'm going to represent that as V1 times T plus V2 times, instead of J, who was that, N, plus V3 times, that's the last element of the basis, instead of K, I have B. So it's the same here. You try to take a vector and decompose that in terms of T, N, and B. Will I put that on the final? No. But I would like you to remember, especially if you are an engineering major, that there is this, or physics major, that there is this kind of Frenet frame. For those of you who are taking a differential equations, you already do some matrices in built-in systems of equations, systems of differential equations. I'm not going to get there. But suppose you don't know differential equations, but you know a little bit of linear algebra. And I know you know how to multiply matrices. You know how I know you multiply matrices no matter how much mathematics you learn. And most of you are not in linear algebra this semester. Only 2 of you were in linear algebra. When I took a C++ course, okay, the first homework I got was to program matrix multiplication. I have 2 given matrices. I have to program that in C++. And freshmen knew that. So that means you know how to write this as a matrix multiplication. Can anybody help me? So T and B is the magic triple. T and B is the magic corner. T and B are the 3 musketeers who are all orthogonal to one another. And then I do derivative with respect to S. If I want to be elegant, I'll put DDS. Okay. How am I going to fill in this matrix? So somebody who wants to know about differential equations, this would be a very good. 0, k, 0, minus k, 0, tau, 0 minus tau, 0. This is called the skew-symmetric matrix. Such matrices are very important in robotics. If you've ever been to a robotics team, like one of those projects, you should know that when we study motions of, let's say that my arm performs 2 rotations in a row, all these motions are described based on some groups of rotations. And if I go into details, it's going to be really hard, but practically in such a setting, we have to deal with matrices that either have determinant 1, like all rotations actually have, or have some other properties, like this guy. What's the determinant of this guy? What do you guys think? Just look at it. 0. It has determinant 0, and moreover, it looks in the mirror. So this comes from a group of motion, which is little SO3, the Lie algebra actually. So what is k is looking in the mirror, it becomes minus k, tau is becoming minus tau. It is antisymmetric or skew-symmetric. Skew-symmetric or anti-symmetric is the same.
Anti-symmetric,
Symmetric.
skew-symmetric matrix.
Skew-symmetric or anti-symmetric is exactly the same thing. They are synonyms. All right? So it looks in the mirror and picks up the minus sign, has 0 on the diagonal. What am I going to put here? You already got the idea. So when Brian gave me this, he meant that he knew what I'm going to put here as a vector, as a column vector. No. How do I multiply? T and B, right? So guys, how do you multiply matrices? You go first row, first column. So you go like this. 0 times t plus k times n plus 0 times b, here it is. Right? So I'm teaching you a little bit more than, if you are going to stick with linear algebra and stick with differential equations, this is good. This is a good introduction to more advanced mathematics. Yes, sir?
Why don't you use the Kramer's rule? Why don't you use the Kramer's rule?
The Kramer's rule.
Yeah, for that matrix.
No, first of all, Kramer's rule is to solve systems of equations that don't involve derivatives, like a linear system like ax equals b. I'm going to have, for example, 3x1 plus 2x3 equals 1, 5x1 plus x2 plus x3 equals something else and something else. So for that, I can use Kramer's rule. But look at that, this is really complicated. It's a dynamical system. At every moment of time, the vectors are changing. So it's a crazy ODE. It's like A of t times something, so some vector that is also depending on time equals the derivative of that vector that depends on time. So that's a ODE system that you should learn in 3351. So I don't know what your degree plan is, but most of you in engineering will take my class, 2360 linear algebra, OD1, 3350, where they teach you about differential equations. These are all differential equations, all 3 of them. In 3351, you learn about this system, which is a system of differential equations. And then you practically say, now I know everything I need to know in math, and say goodbye math. If you guys want to learn more, of course, I'm happy. I would be very happy to learn that, hey, I like math, I'd like to be a double major. I'd like to be not just an engineering, but also math major if you really like it. Many people already have a minor. Many of you have a minor in your plan. Like, for that minor, you only need
One extra math course.
one extra math course. For example, with 3350, you don't need 3351 for a minor. Why? Because you are taking the probability and stats anyway, you have to, right? They force you to do that, 3342. So, if you take 3351, it's on top of the minor that we give you. I know because that's what I do. I look at the degree plans, and I work closely to the math advisor with Patty. She has all the degree plans.
So as an engineering degree, to get a second degree, as you say, how many classes?
You mean double degree? We have this already in place. We've had it for many years. It's an excellent plan. 162 hours it is now. It used to be 159. Double major, computer science and mathematics. And I could say they were some of the most successful in terms of finding jobs. They took what would you take on top of that? Well, as a math majors, you have a few more courses to take on top of that. You can link your computer science with the mathematics, for example, by taking numerical analysis. If you love computers and you like calculus and you want to put together all the information you have in both, then numerical analysis would be your best bet. And they require that in your computer science degree if you are a dual major, and your math degree. So the good thing is that some things count for both degrees. And so with those 160 hours, you were very happy. And then I got a few more hours. Many math majors already have around 130. They're not supposed to. They're supposed to stop at 120. So why not go the extra 20 hours and get 2 degrees in one? Yeah. Of course, it's a lot more work, but we have people who like, really, they are nerdy people who love computer science from when they were 3 or 4. And they also like math, and they said, okay, I want to do both. Okay, a little bit more, and I let you go. Now I want you to ask me other questions you may have had about the homework, anything that gave you headache. Anything that you feel you need a little bit more of an explanation about. Yes.
I just have one. In my work, what is the easiest way to take the square root of something?
SQRT.
SQRT is what you type.
Thank you.
And but of course you can also go to the caret 1/2. Something non-technical. Any question? Yes, sir. From the homework, or a relation to that?
I don't understand, why is like the tangent unit vector, it's just the slope off of that line, right? The drunk bug, whatever line the drunk bug is on?
So it would be the tangent to the direction of motion, which is a curve, and normalized to have length 1, because otherwise r prime is, you may say, why do you need t to be unitary? Okay. Computations become horrible unless your speed is 1, or 5, or 9. If the speed is a constant, everything else becomes easier. Okay, so that's one reason.
And like, why is the derivative of t then perpendicular? Why does it always turn into...
You mean perpendicular to t?
Yeah.
We've done that last time, but I'm glad to do it again. And I forgot what we wrote in the book, and I also saw in the book this thing that if you have r in absolute value constant, prove, and I've done that with you guys, prove that r and r prime at every point are perpendicular. So if you have, we've done that before. Now, what do you do then? T dot t is 1, scalar dot product, t prime times t plus t times t prime, so 0, okay? And t is perpendicular to t prime, because that means t dot t prime equals 0. When you run in a circle, you say, okay, that's good. Run in a circle. Right? I say, this is my t. I can feel that there is something that's trying to bend me this way. That is my acceleration, and I have to. But I don't know how familiar are you with the winter sports. In winter sports, in many winter sports, the Frenet trihedron is crucial. Imagine that you have one of those slopes and all of a sudden the torsion becomes too big. That means it becomes dangerous. That means the vehicle you're in on a snow vehicle or any kind of your ski slope, if the torsion of your body moving can become too big, that will be a problem. So you have to redesign that slope. And this is what they do. You know there have been many accidents, and many times they say even in Formula One, the people who project a certain racetrack, like a track in Indianapolis or Monte Carlo or whatever, they have to have in mind that Frenet frame at every second. So there are simulators showing how the Frenet frame is changing. There are programs that measure the curvature and the torsion for those simulators at every point. Neither the curvature nor the torsion can exceed a certain value, otherwise it becomes dangerous. You say, oh, I thought only the speed is a danger. Nope. It's also the way that the motion, if it's a skew curve, it's really complicated because you twist and turn and bend in many ways, and it can become really dangerous. Speed is not everything. Okay?
You said the torsion was the twist, like the twist of the track?
The torsion is the twist. And by the way, keep your idea. If you wanted to ask something more, when you twist, okay, suppose you have something like a race car, and the race car, these are the walls of the track, and here's when you have a
Banked curve.
a very abrupt curvature and torsion, and you can have that in Formula One as well. Why do they build one wall a lot higher than the other? Because the poor car, I don't know how passionate you are about Formula One or car races, but the poor car is going to be close to the wall. It's going to bend like that. That wall will be round, and you have to, as a builder, you have to build the wall really high, because in that kind of high speed, high velocity, high curvature, the poor car is going and then again on a normal track. So if the wall, imagine what happens if the wall is not high enough. The wheels of the car will go up and get over, and it's going to be a disaster. Right? So that engineer had to study all the parametric equations and all the Frenet frame in detail, make a simulator, compute how tall the wall should be in order for the car not to get over on the other side or get off the track. It's really complicated stuff. I mean, it's all mathematics and physics, but all the applications are run by engineers. And yes, sir?
What's the difference from centrifugal force?
The centripetal force is related to R double prime. R double prime is related to N and T at the same time. So at some point, let me ask you one last question, and I'm done. What's the relationship between acceleration, R double prime, and N? Are they the same thing, and when are they not the same thing? Because you say, okay, that practically the centripetal...
They're the same on a curve.
They are the same
Like on a circle.
on a circle, and you are getting so close, it's hot, hot, hot. On a circle and on a helix, they are the same up to a constant. So what do you think the magic answer will be? N was what, guys? N was, remind me again, that was T prime over absolute value of T prime. But that doesn't mean that's not equal, in general, that's not equal to R double prime. When is it equal? In general, it's not equal. When is it equal? If you are in arc length, and you see the advantage of arc length is wonderful. In arc length, T is R prime of S. And in arc length, that means T prime is our double prime of S. And in arc length, I just told you T prime is the first Frenet formula will be curvature times the N. So the acceleration practically and the N will be the same in arc length up to a scalar multiplication. But what if you are not, your speed is not even constant? Then God help you, because the acceleration are double prime and N are not collinear. So if I were to draw, and that's my last picture, let me give you a wild motion here. You start slow, and then you go crazy and fast, and slow down again. So just like most of the physical models from the bugs and the flies and so on, in that kind of crazy motion, you have a T and N at every point, and a B. Let me change, yeah, a B will be down, and T is here. So can you draw arc double prime for me? Will still be towards the inside, but it's not going to coincide with N. It may be this one. What's the magic thing is that T, N, and R double prime are in the same plane, always. That's another secret other students don't know in Calculus 2. That same plane is called osculating plane. We have a few magic names for these things. So T and N, the plane that is, how shall I say that? I don't know. The plane given by T and N is called osculating plane. The acceleration is always on that plane. So imagine T and N are in the same shaded plane, R double prime is in the same plane. Okay? Now can you guess the other two names? So this is T, this is N, and T, and B is up, is my body's direction. T and N, look at me, T, N, and B. I'm the Frenet trihedron. Which one is the osculating plane? It's like the horizontal XY plane. Okay, do you know, maybe you're a mechanical engineering major, and after that I will let you go. No extra credit though for this answer. Maybe I'm going to start asking questions and give you $1. I used to do that a lot in differential equations, like ask a hard question, whoever gets it first, give $1. Until a point when they asked me to teach honors 3350, when I started having 3 or 4 people answering the question at the same time, and that was a significant expense because I had to give $4 away at the same time.
I feel like you should have just split it.
So, tangent, normal, and binormal. Does anybody know, this is me, the binormal, and this is the normal. Does anybody know the name of this plane between normal and binormal? This would be this plane. Normal and binormal. They call that normal plane. Okay, so it's tricky if you are not a mechanical engineering major, but some of you are, maybe we'll learn that later. Any other questions for me? Now, in my office, I'm going to do review. I was wondering if you have time. I don't know if you have time to come to my office, but should you have any kind of homework-related question, I'll be very happy to answer it now. 3 to 5. And now, one time I had a student who only had 7 questions left. He came to my office and he left with no homework. We finished all of them. And I felt guilty. But at the same time, he said, no, it's better I came to you instead of going to my tutor. It was fun. So we can try some web work problems together today if you want, between 3 and 5, if you have the time. Some of you don't have the time. All right? If you don't have the time today and you would like to be helped on web work, what do you do? Click email instructor. I'm going to get the questions by you. You may ask me anything at any time of the day. Yeah.
I wanted to apologize and thank you for giving me that information. I take little difficulty.
That scared me. It was just like a solid punch.
No, you were not.
Oh, I
Why are
was
you
just trying to
saying
decide to the wrong
that?
class.
Okay.
I figured that out, I was like, oh, wait, that's not my class. So, yeah. And second, I wanted to apologize because I did not bring my spiral today. So it, my notebook. So I didn't take my notes, and I remember that always made my
But you know
my Cal 1
what?
teacher very mad.
I have somebody who's taking notes.
Yeah, I know, and
He's
that's why I was
gonna
like,
make a copy and I'll give you a copy.
yeah, but I always my Cal 1 teacher, Dr. Henry, was our teacher.
Yes,
Have one.
yes. Have a nice day.
He was always really mad when I didn't take
Yeah, I
notes,
know.
because he felt like I was not. I guess